Hello students, this is Dr. DiVincenzo. This is your first video for general chemistry, and since it's your first video, let me explain to you the purpose of these videos. They are basically a supplement to cover some of the fundamental and basic stuff that's within your textbook and in your slides, and the idea is to basically get you moving on the material outside of the classroom so that I can spend more time in the classroom on more difficult concepts and problem solving. So if I covered in the video, I don't typically spend a lot of time in class on it unless there are questions and concerns, or we have maybe examples, or we do some problems in class. So that's the essence of it. So this is your chapter 1 video, and this is what I'm going to cover in this video. I'm going to talk about a scientific theory, some of the laws, some formulas and modules, metric units, temperature conversions, significant figures, and unit conversions. And we'll definitely do some significant figures and unit conversions in class. But there'll be more like questions and practice than they are going over some of the fundamentals. That's the idea of these videos. It's a bit of a flip classroom, getting you doing some of your learning outside of the classroom so we can spend more time, high quality time in the classroom. So what do you think about what a scientific theory is when you think about a theory? When you think about the famous theories, the ones that might pop into your head are evolutionary theory, Big Bang theory, atomic theory. Those are the three big ones that pop into my head based on my training and my background. Those are the ones that I tend to think of. There's many others you can think of. Now, when you look at the scientific method, you realize that, theory falls over here. It's the end of the scientific method. You see this other word model here. Okay, and it's after you've, had your observations, you've done your tests, you've looked at your data, you've analyzed those results. Now, a model you might consider kind of another word really for a law. You notice law does not appear anywhere on here. So when you think about a law versus a theory or a model, what does that mean? Well, think about a classic law. This is like Newton's second law of motion, F equals ma. Force equals mass times acceleration. Okay? And a law is there to model the data. So if you will, I can do a prediction in which I apply a particular force to an object that weighs a certain mass. I can then predict what its acceleration is going to be. And we've done this repeatedly. We know that this equation, this model, this law holds under all conditions. It doesn't matter if we're talking about a ball in a person's arm, or a truck and a rock, or a planet. It holds under all those conditions, except for under conditions of where quantum theory overtakes these laws, and that's going to be on very small particles, things like electrons and how they move, but that we'll cover in chapter 3. So for this is the idea of a law, and it doesn't attempt to explain anything. It doesn't explain why the force produces acceleration, it doesn't talk about the inertia, the mass, friction, or anything like that. It just models the data, it makes a statement, and there it is. And you can interpret it different ways. You can interpret it from the idea of the acceleration. You could say, for a given acceleration mass, what's the force that's applied? Now, a theory, when you think about these big theories like evolution, Big Bang, you think about something that has much more than a law. It's this broad explanation that might include, part of the process of the explosion and the movement of matter and the formation of things might include this law or this model as part of it, built within evolutionary theory, in addition to, gravitational attraction and energy expansion and all of this. And then we might try to explain, let's say we don't have a lot of data. That's representing my Big Bang in time. Let's say we don't have a lot of data in the first 10 minutes after the Big Bang. As we get more data in this space here, as astronomers make more observations, make more measurements, we get more data, we modify that theory. We change it. Maybe we change some things that we said about this period right here, and we adjust it. It's moldable. It's meant to be flexible, and it's going to explain what's going on. That's really the distinction between a law or model and a scientific theory. And anyone who tells you a scientific theory is fact is not being, on the up and up with you. There are facts contained within that theory. things that are maybe indisputable, at least for what we know right now in the scientific data. But the theory itself is meant to change and mold. And when I say change, it's not anything like the whole thing's going to flip on its head. Just take a look at what happened with physics, okay, with Newton's laws and what we call classical physics, okay, electricity and magnetism. Quantum theory came along where the idea was that, hey, a lot of this stuff that we know doesn't apply to electrons and particles and atoms. So do we throw out all these laws? No. We simply modify them and say, okay, they no longer apply. These theories of magnetism, electricity, and gravitation, they no longer apply to things at a very small level. We have this new theory now called quantum theory we're going to use to explain things at a very small level. So that's the idea of how these theories work, come about, change, and mold. I want to make that distinction because lots of times the textbooks aren't real clear and there are some discrepancies. Now, these are two of the laws that are important in your first chapter: law of multiple proportions, law of definite proportions. I guess there should be an S there. And I'm not a big stickler on asking you to regurgitate a particular law. What I want you to do is understand what we get from them. So I might ask a question about, is this true or false, or is this, which of these statements is valid based on our known laws? That type of thing, rather than saying, hey, regurgitate the law of definite proportions. So what these are basically saying is that, hey, there's another one too, law of constant composition. I don't think that one's in your book. But anyway, the idea is that no matter where I get H2O from, the Nile River or the Stones River, it's going to be two hydrogens bound to oxygen. Okay? And that's not going to change. That's the definition, if you will, of a compound. And it's always going to contain the same proportion by mass, too. Because each of these hydrogens weighs a certain amount, and each of the oxygen weighs a certain amount. It has the same proportion by mass. Now that might seem pretty obvious, but realize several hundred years ago it wasn't obvious, and we were uncovering what matter was composed of. We didn't know what compounds were, atoms were. That's what we're uncovering. Now it makes kind of sense. Yeah, obviously H2O is H2O. It's always going to have two hydrogen, one oxygen. Therefore, the mass ratio is always the same, right? That should make sense to you. This one's a little trickier, but it's really not that bad. It says when we have two different masses of one element react to given a mass of another element, the two masses of the first element must be small whole number ratio. So the idea is that, if we can form a compound from two different elements, two different compounds, it's another way of wording it, that when it's possible to have two different masses of one element, so these are the two different masses of oxygen, react with a given mass of another element, that's the other element, it's the same in both, just one mass. So here I've got it symbolized as an atom, but think about it as a mass. I have a bunch of carbon atoms, okay? The two masses of the first element must be a small whole number ratio. So the idea is that this ratio here is going to be comparable to this one here. Let's just take the masses. It's 12 to 16. Those are the masses we now know. Okay, if that's a one-to-one relationship, we say, in terms of masses, let's say we had, right, then this must be 12 to 32 because there's two of these. I'm doing it on the atom basis to explain it, but they figured this out in a bulk matter way. That is obviously a 2-to-1 ratio, where this would be our 1-to-1 ratio. It's kind of all this is saying. And that should, now that I've explained it like that, should make sense to you. Of course that's the case if oxygen weighs a certain amount. It's just imagine these are Lego blocks. I'm combining one black with one yellow and one black with two yellow. Well, that ratio of masses is going to be a whole number ratio is what we're saying. All right. A couple ways we can represent chemistry, formulas and modules. So here's a molecular formula. And you notice these don't necessarily have to be in any sort of order. It just groups the atoms. C3, H6O. It doesn't tell you anything about the structure. Now, sometimes you might see something written like this. So it tells you a little bit more about the structure. You see this group of CH3 here, group of CH3, and there's the CO. But it doesn't have to be written that way. Structural formula is actually showing you much more than even this does. This shows you kind of the grouping, but it doesn't really show you the bonding. Here you see a double bond. Condensed is once you get good at chemistry, you know, hey, a CH3 group looks like this, so you don't have to write it out. You write this more condensed formula. Ball and stick models, you'll use those in organic chemistry. I'll show you a few when we get further on into the semester when I want to show you some things. And then this is a space filling model where the bonds are not actually shown. They're shown more as like groups of electron clouds. That'll become more clear as we move over. Move on. Here's metric prefixes that are also part of our outline. We said we're going to cover metric prefixes, metric units. So these are prefixes, and this is the table in your book. Table 1-1. And kilo, centi, milli, micro, nano, pico, the ones we're going to deal with mostly. That's supposed to be pico there, not femto. Now, you might see femto, you see atto in the book, and they might be used. I'll try to keep my quizzes and exams to these ones I've highlighted. These are the big ones that we use a lot, and you should be familiar with. And so that's the prefix, and that's the exponential notation for those. Okay, so, if you will, milli is 10 to the minus 3, so a millimeter is 10 to the minus 3 meters, or 0.001, moving it over 3 places, like that, right? You gotta get familiar with this metric system. We'll spend some time in class doing examples, but I really need you to kind of learn what these mean, and also know how to go from like 1 meter to nanometers, and how to go from 30, picometers to meters. How many meters is that? Get comfortable going back and forth between these. Okay? And I always teach my students in my lower level classes sometimes to think about like a dollar, the money system. $1, 25 cents, and 5 cents. If I'm converting from 5 cents to a dollar, the number's going to get smaller, right? Because dollar's a bigger unit. If I'm converting from dollars to cents, hey, how many nickels are in a dollar? Well, there's 20. How many dollars are in a nickel, right? Then it's going to be a fraction. Okay? So that's this is in a way the same thing grouped that way. If I'm moving up or down, think about the number, how many places you're moving. And if I'm not doing a meter, say I'm going from a nanometer to a centimeter, well, just look at how far they're apart. Nano and centi, 10 to minus 2 and 10 to the minus 9. So they're 7 apart. So 7 places will change depending if you're going in this direction or this direction. Okay? So just get familiar with that metric system. Now, temperature scales, we're going to use mostly Celsius and Kelvin, and majority of the time Kelvin, but also Celsius. And you're all familiar with this. So this is the equations allowing you to convert. So sometimes people will give 2 equations, one going from, if you got your temperature in Fahrenheit, you get Celsius, or if you got Celsius, you get Fahrenheit. There's no need to do that because you can plug it in anywhere and just solve for it. So what I'm going to do is to show you here the way we do this. Let's take a number we know, 212 degrees Fahrenheit. Always use a number or you can use 100 degrees Fahrenheit, because those are, I'm sorry, not 100 degrees Fahrenheit, 32 degrees Fahrenheit, freezing and boiling. Because the answer to that in Celsius is 100, so you can test and make sure you've done the math right. So let's take this 212, we got 5/9, and that's going to be 212 minus 32. So you got 212 minus 32 gives us 180. So it's 5/9 times 180. So it's 180 times 5 divided by 9. And I get that's equal to 100. then you can just add 273 to get to Kelvin. That's easy. If you had Celsius, well, then you'd do it the other way. You'd have 100 Celsius and get rid of the 5/9 on both sides, so it'd be multiplied by 9/5. So it's 9/5 degrees Celsius, and then you would add the 32, right? So that one's not going to be the parentheses. You do the 9/5 plus, so it becomes 9 times 100 divided by 5 plus 32, and that's going to give you 212. Okay, so that's your temperature conversions. Significant figures. Now, significant figures, and you'll see all the rules. I've got slides on the rules and all of this. And the purpose of significant figures is to give you an indication of the precision of the number. So let's say I tell you I've got 3.0 grams, okay? And someone needs that converted to nanograms. Okay, so it's now 10 to the minus, let's just do micrograms, 10 to the minus 6. So it becomes 6 places. So 1, 2, 3, I'm sorry, I did it the wrong way. I want to go from, let's make this originally 3 micrograms. I want to convert it to grams. So it's 1, 2, 3, 4, 5, 6. It becomes 0.000003, right? 1, 2, 3, 4 grams. And that's micrograms. Now, you've added a bunch of zeros. I should put a 0 back here, actually, because it was 3.0. You've added a bunch of zeros, but that's just placeholders. These are not significant. They're just placeholders. Okay, they weren't in the original measurement. My original measurement only had 2 digits there. And now all of a sudden I got all these extra digits. So that's why we would report this as 3.0 times 10 to the minus 6 grams, showing us that, hey, we've only got 2 digits of precision. These things are just placeholders. So when you have numbers 0.052908, zeros that are placeholders are not significant. But this one is significant because it's in the middle of a number. Okay, so what you're doing is you're thinking about weighing something on a scale and how precise that scale is. So imagine a scale that gives you, here's my scale, and it only gives me 2 places after the decimal. Let's say this is a grams. Okay, and we get a number of 2.31. Now keep in mind, this number here is considered significant. This is 3 significant figures, but this is the one with uncertainty. The last one is the one with uncertainty, even though it's still significant, because we don't know what the scale, the actual weight that we put on the scale was. Maybe it was 2.309, and since the scale doesn't show you this, it rounds it to 3.1. But my scale's not precise enough to know that. So now if you got another scale with another digit, couple digits here, that gives you more precision, you see? So with any number, the last digit is imprecise. Is uncertain, I should say, is the correct word. So that's what significant digits are. And we'll go over in class how you use them in calculations. But I want you to realize that, any number is significant. Okay, 3, 2, 1. And then within a number, zeros are significant if they're wedged in between or if they're after. I could put another one here. Let's do another one. Let's do 2.306090. This zero is also significant. Any zeros after the decimal place once you have a number. This one is not because it's just a placeholder. But this one has to be significant, and this one is also significant once we have a number there. Okay, so you can look at those rules in your book. And the last thing I want to do is unit conversions. And this will knock out the video. I try to keep these to under 30 minutes, preferably around 20. So, if I have 3 meters, and I want to convert that to millimeters, so you can say times 10 to the 3 millimeters in 1 meter. Or you can say times 1 millimeter is 10 to the minus 3 meters. That's using the prefixes that are here. So our brains don't work as good like that, I don't think. And I'm more comfortable with things like this, so that's the way I do my conversions. But this is going to show you meters cancel out and you're left at millimeters. It gives you the same answer. It's 3,000 in both cases. Both cases, the meter cancel out. Okay? So it's important. It's called dimensional analysis, and just setting up this to get to what you're interested in. So if I tell you I've got 26.2 micrometers, and I want to know how many nanometers that is, well, micros 10 to the minus 6 and nanos 10 to the minus 9, so they're a factor of 1,000 apart. So you can either do 26.2 micrometers times 10 to the 3 nanometers in 1 micrometer, right? And your answer is going to be 26.2 times 10 to the third. Or you could do it as 26.2 micrometers times 10 to the minus 3 micrometers in 1 nanometer. Like that, you still get the same answer. So that's my idea of just showing you some of those basic metric conversions within the metric system. Going between systems, well, then you got to have a conversion factor, and that's something we'll practice a little bit in class. With that concludes the end of our first video, Chapter 1.